Yeah, this is a small class of 10 students, but they're the ones who usually attend. Yeah, so they were good.
Okay. Thank you, sir.
No problem. Yes. Good morning. Hey, good morning. So today we're going to start a new topic on transportation and assignment problem topic, and this is a specific application within linear programming and operation research. A well-studied problem, very practical, especially if you're going to be looking at working in a type of logistic environment. Basically, the transportation problem is used to plan for the distribution of items between, let's say, a warehouse and a store. So our focus today is going to be into looking at this specific transportation application and also the assignment problem, which is a special case of the transportation model. So in addition to that, we're gonna start discussing the integer programming topic, which I mentioned at the beginning of the semester, that at some point we were going to learn how to solve these problems that needed to have solutions that were integer in value. Like so far, we've been solving problems using the simplex method, and for those problems that most of the time we were getting solutions that were fractional numbers, but we know that there are certain problems in which we need to have an integer solution for our decisions. So we're gonna learn how to work with those type of problems also. We're gonna start that discussion today. So let's begin with the transportation topic. And this is all part of we've been going through all this semester. We get into that last objective, which is to recognize, analyze, formulate, and solve industrial problems that can be dealt with linear programming. So this transportation problem, the assignment problem, is again one of those problems that is very practical and that you might see a lot if you're working in the logistics area within industrial engineering. And today we're gonna discuss two special types of linear programming problems. The first one, transportation. The assignment, as I mentioned, is a special case of the transportation problem. So we're gonna start with the transportation, and then we're gonna basically make a distinction in terms of what is different when you're solving the assignment. And the agenda for today is to look at the definition of the transportation model. And then we're gonna talk about what is the balanced transportation problem. And finally, we will discuss the assignment. So let's start with the definition of this type of model. The general description of the transportation model is a problem that deals with the problem of finding the best way to fulfill the demand of n demand points using the capacities of m supply points. So the idea, again, if you think from a practical perspective, you have an n number of warehouses and you have n demand points. They could be stores, this could be customers, and then you're trying to supply those nodes, those demand nodes from the supply nodes. Obviously, your supply is gonna have some limited capacity. So it's not like you can have a single point to supply every single customer. So if your warehouse can only supply 10,000 items and you have a demand that's above that, then you know that you're going to have a shortage in terms of supply. But in this problem, we're going to look at those cases. We're going to assume first that we have a balanced problem in which we have enough to supply each demand node. And then we're going to look at the unbalanced problem and see how that is solved. Generally, a variable cost of shipping the product from one supply point to a demand point is taken into consideration. So for example, we have multiple supply points, we can have a cost associated with the distance from a warehouse to demand points like stores. So there could be a cost associated with the gas, could be a cost associated with, I don't know, anything that you are considering as a cost to your company. So most of the time we use distance, or we use the cost associated with the traveling from point A to point B. So why is this important? We want to find the best way from this perspective, the minimal cost in which you can serve all this supply or demand, these demand points by minimizing the cost associated with transportation. So generally, we're going to have a variable cost of shipping the product from one point of demand to a demand point, and we're going to take that into consideration. So the reason I'm bringing this slide is because when we think about transportation, the transportation problem, sometimes we just think about distribution from a truck. But the transportation problem can also be applied to a supply chain for power. It's the same idea. You have some generation, and then you have a network in which you're going to decide who's going to supply your customers. So again, there's going to be a cost associated with serving specific demand points, and you want to find the best or the minimal cost as network associated with the distribution. So we're going to use this example to illustrate the problem. So we have PowerCo has 3 electric power, the electric needs of 4 cities. The associated supply of each plant and demand of each city is given in this table. So we're gonna have 3 plants, plant 1, 2, and 3, and you have a supply in terms, this is your capacity in terms of million kilowatt hours. And then you have 4 cities. Each one of them have a demand. So 45 also a million kilowatt hours, 45, 20, 30, and 30. You can also see that there's a associated cost for supplying from each one of these plants to each one of these cities. If you look at plant 1, city number 2 is the less expensive path. So plant number 1, if you choose plant 1 to serve city number 2, you're only paying $6. Plant 2, same thing. There's some variable cost associated with each one of those cities, and also for plant number 3. So the question is, you have this capacity for each one of these plants, and then you have this demand for each one of these cities, and you want to find the best way to serve that demand, which is less expensive for you. So the transportation problem is specified by the supply, the demand, and the shipping costs. Okay, so we have all that information here. We have the demand, the supply, and the shipping costs. The relevant data can be summarized in a transportation tableau, which is what we have in the previous slide. And the transportation tableau implicitly expresses the supply and demand constraints and the shipping cost between each demand and supply point. And so we're going to have a constraint or some constraints associated with the supply. Those are going to be defining our capacity in terms of service. And then we're going to have some constraints associated with the demand, which are going to express a minimum bound for the amount of energy that we need to receive in order to supply the needs of a specific city. So again, this is going to be our transportation tableau, and we have the shipping costs, the supply, the demand for this company. So to formulate the problem, we're going to start by expressing our decision variable. So if you were to specify this decision variable, how would you define this decision variable? We're going to use two indexes, I and J. So one of them will be used for specifying city, the demand city, and J will be the supply node, right? So Xij is used to define the amount of electricity produced by at plant I that is sent to city J. So this decision variable will allow us not only to supply from one node, but we can also, this supply node can also serve multiple cities. Not that one supply node will only serve one city, but also can serve multiple cities in the network. In the same way, we can also have a supply, multiple supply nodes serving the same city. Okay, so we have that possibility, and that's why we have these two indexes defining our decision variable. So for instance, if we have X14, this is the amount of electricity produced at plant 1 and sent to city 4. So X14 is telling us, okay, this is the amount of energy or electricity that I'm sending from plant number 1 to city number 4. We change 4 by, and instead of 4, we have 3, then from plant 1 to city 3. Obviously, these numbers are going to be associated with a specific city name, but for the purpose of modeling, we can just use the numbers. So we solve to, in terms of the objective function, we solve to minimize the total cost of shipping from plants to cities. And that cost is going to be associated with these numbers that we have for the network, or the shipping cost associated with each plant and each city. So you can imagine that as we grow the number of cities and the number of plants, this objective function is going to be very, very big. Even with this small size problem, in which only have 3 plants and 4 cities, you'll see that this equation is going to be kind of long. So if we look at the indexes, this is going to be 1, 1. This is going to be 1, 2, 1, 3, 1, 4. This is going to be 1, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 4. So we have 12 decision variables in this problem, and we're going to state those that objective function based on those 12. So if I look at decision variable 1, 1, the cost associated with that path is $8. Then I have the path from 1 to 2, $6 X12, plus $10 X13, plus $9 X14. So I got the first path, the path from plant 1. Then I move to the next plant, have 9 x21 plus 12 x22 plus 13 x23 plus 7 x24 plus 14 x31 plus 9 x32 16 x33 plus 5 x34. And that will be our objective function. Again, 12 decision variables. We have an arc associated with each supply and demand node. This is basically having something like this. You have 3 nodes, 4 demand points, and you're trying to decide how to ship all this power from each plant to each city. So we have an arc associated with each path, and we have a cost associated with each one of those arcs. Any questions? Okay, so this will be one, two, three, and then you have 1, 2, 3, and 4. These are the demand, and this is the supply. But we know that each supply node has a limited production capacity. So we have to define a constraint associated with that capacity limitation. So our constraints, as I mentioned already, we have 2 groups. One group will be looking at the supply. Second group will be looking at the demand. So the supply constraints, which are the ones associated with the supply nodes, we're going to have 3 of them, and they're going to be tied to this supply capacity. So this is the supply capacity, meaning that plant number 1 can only supply up to 35 million kilowatt hours. Plant number 2 can only supply up to 50 kilowatts, million kilowatt hours, and plant number 3 can only supply 40 million kilowatt hours. So I'm going to define a constraint in terms of those capacities. For the supply, the first one has to be less than 35. Second one has to be less than 50. And the last one has to be less than or equal to 40. Because those are the capacities associated with each one of those plants. Question now is, what is the left side? So the left side is going to be associated with the cities that you are going to be serving. And you're going to be looking at the decision variables that are associated with the plant number, in this case, plant number 1. So those are going to be, you're going from 1 to 1, from 1 to 2, from 1 to 3, and from 1 to 4. So those are the decision variables that you want to have on the left side of the first constraint. So you're supplying from supply node 1 to city 1, plus you're supplying from supply node 1 to city 2, plus you're supplying from supply node 1 to demand 3, plus you're supplying from 1 to city 4. So the summation of those decision variables, which are again the amount of energy that you're supplying from plant 1 to city number 1, 2, 3, 4. Summation of those has to be less than or equal to the capacity, which is 35. And we're going to do the same process with the second constraint. But instead of looking at I index equal to 1, we're going to look at I index 2. So 2, 1, 2, 2, 2, 3, and 4. So everything that goes from 2 to each one of these cities, summation has to be less than or equal to 50. And then we go to the next one, 3231 plus x32 plus x33 plus x34. And everything has to be less than or equal to 40. Very simple, okay? Now we have a second group of constraints, and these are associated with the demand. So you see at the top, we have a subtitle here. So first group, supply constraints. Second group is the demand constraints. So now, how would you formulate, let's say, the demand constraint for the first city? Yes, both of you are right. Yes, so now you're looking at, I'm in city number 1, and I want to know who's supplying to my city, right? So it could be supply 1, supply 2, or supply 3. You're correct. It's they're the same in terms of formulation. We're both formulating, but the format of the formulation is different. Yes, it's different. So now we're using every single decision variable, and you'll see that for each one of those supply and demand nodes, the constraints are going to be similar in terms of size. You're going to be using the same number of decision variables. The only thing that is going to be changing are those index, which are associated with the specific city that you are working with, or with the specific supply node that you're working with. And so in this case, we're going to go down the column as you mentioned. So for the first constraints, we're looking at the rows. Now we're going to be looking at the columns. So we're going to look at the demand for city 1. You want to satisfy this demand by using plant 1, plant 2, and plant 3. Okay. So the solution of the problem would tell us, even though you're setting up your constraints in this way, you're going to be using only, let's say, plant 1 or plant 2 or both or all of them. So it would depend on how the cost plays out in terms of the final solution. But in this case, we're going to have, and that's the other important characteristic, since we have 3 supply nodes, we're going to have 3 constraints, and we're going to have 4 cities. So we're going to have a constraint for the demand. We're going to have a constraint for each city. So a total of 4 constraints. So this is x11 plus x21 plus x31. And then this is going to be 45. x12 plus x22 plus x32, 20, x13 plus x23 plus x33, 30, x14 plus x24 plus x34, 30. The question now that I have for you now is the sign for this constraint. Would this be less than or equal to, greater or equal to, equal to? How would you set up this? Yeah, those are good questions. So first, let me address the less than or equal to sign. If you set up this in this way, and you are trying to minimize, what you are going to obtain is a solution that is going to tell you the best thing to do is make them equal to 0, because you're not forcing them to at least supply certain amount of energy. You make this decision variables equal to 0 and you have less than or equal to, this constraints will be satisfied. Okay, so, and the other ones will be satisfied as well because you have a less than or equal constraint. So everything, making everything equal to 0 will make the solution, since you are minimizing, will make the solution equal to 0, and it's a feasible solution. That's not what we're trying to do. So that's why we don't have a less than or equal to, because that solution basically is not forcing the problem to satisfy the demand. The second question was, why don't we make this an equality? The reason for that is, if this problem is not balanced, meaning that you don't have a same amount of supply and demand, let's say 70 and 70, if you have 70 and 70, that means the problem is balanced. You have the same amount of supply, same amount of demand, then you will be able to find a solution for the problem with the equality constraints. But if you don't have, if you don't have a balanced problem, then this problem will become infeasible, because you know for sure you're not going to be able to meet one of those demands, or you're not going to be able to have the same amount of supply and demand. I don't know if that makes sense.
Yeah.
Yeah. So best way to model this would be, instead of using an equality, will be to use a upper bound or lower bound, which means that you want to have at least 45 amount of energy supplied to this city. At least 20, at least 30, at least 30. But obviously, since we are minimizing, you will see that this side of the constraint will be making this equal to 45, this equal to 20, this equal to 30, and this equal to 30 as well. Because going above that number will add an extra cost. Okay, so from a modeling perspective, it's not wrong to say they should be equal to. Problem is, if you don't have a balanced problem, solving the linear programming model will throw you an infeasible solution, because you are not going to be able to get the same amount here and here. With an unbalanced problem, you can work out, if you have more supply than demand, you still can get a solution. The problem is when you don't have enough supply, and we're going to talk about that now. But from this perspective, again, what I want you to understand is, problem is not difficult to formulate. You have decision variables associated with each arc in the network. You are minimizing in this problem. You want to minimize the cost associated with the transportation. And then we are doing the minimization of all the arcs and the cost associated with those arcs. We have two groups of constraints, one for the supply, one for the demand. And we want to make all those decision variables greater or equal to 0. And that's a formulation. So this is the whole formulation for the problem. Any transportation problem, you formulate it this way. Okay, so if you're faced with a transportation problem, you don't have to think about how to formulate the problem. This is the template. Obviously, it's going to be different as you have more or less supply nodes and demand nodes, but the template for the problem is this one. So let's talk about another example. And now we're going to look at those cases in which we have unbalanced demand and supply. So this is a second example. Now we have NG Auto has 3 plants in Los Angeles, Detroit, and New Orleans, and 2 major distribution centers in Denver and Miami. The quarterly capacities of the 3 plants are 1,000, 1,500, and 1,200 cars. the demand at the two distribution centers for the same period are 2,300 and 1,400 cars. The mileage charge and transportation cost per car between the plants and the distribution centers is given here. So we have the mileage, and we also have the transportation cost per car between the cities and the supply centers. So Denver and Miami are your supply centers now. So you have those at the top, and the cities that they're serving are Los Angeles, Detroit, and New Orleans. I'm sorry, the opposite. The three plants in Los Angeles, Detroit, and New Orleans, the major distribution centers are in Denver and Miami. So our network is going to be similar to the one I showed you for the first problem. You have the sources, you have the destinations, and then you have a cost associated with the arcs. And each arc will go from each source to each destination. So for the definition of this model, again, we have our transportation Tableau at the bottom. So we want to formulate this problem using this information. So again, we're going to follow the same template. We're going to minimize Z, and we have the cost associated with each arc. So we have 6 decision variables and 6 arcs. So we have 80 x11 plus 2 15 x12 plus 100 x21 plus 108 x22 102 x31 plus 68 x32. And we're going to have a group of constraints that are going to be associated with the supply, and a group of constraints that are going to be associated with the demand. So we have x11 plus x12. This is the supply. 1,000. Then x21 plus x22. So this is for Angeles, and this is for Detroit. And then we have the demand. So this is x31 plus x32 greater or equal to 1,200 . Let me. So we have 3 plants, right? So these are our supplies, right? So, and we have sorry. Yeah, so that should be less or equal to, sorry. So these are the supplies. And then we have the demand. So we have x11 plus x2, 1 plus x3, 1 greater or equal to for member, and this is for your means. We have x12 plus x22 plus x32 greater or equal to and then we have all xij's greater or equal to 0 for I equals 1, 2, and 3, and j equals 1 and 2. So as I mentioned, it's the same format, right? We have a group of constraints for the supply. We have the group of constraints for the demand. And we have the decision variables. All the decision variables are using the objective function. We are trying to minimize these costs. So that basically takes us to the general description of the transportation problem. We have a set of M supply points from which a good is shipped. Supply point I can supply at most SI units. A set of N demand points to which the goods is shipped. Demand point J must receive at least DI units of the shipped good. Each unit produced at supply point I and shipped to demand point J incurs a variable cost Cij. So using these parameters, or defining these parameters Si, Di, and Cij allows us to set up the problem in general form. Okay, so there's no numbers here. We have the description of the transportation problem. You have an objective function that is defined in terms of cost of Cij, of that arc from I to j, times the number of units that you're moving, which is Xij. And then you have two group of constraints, one for the supply, Si, for all i's in I, which is the set of supply nodes. And then we have a group of constraints that are defined for each j. J is the demand points. So depending on how many demand points you have here in this set, you're going to have a specific number of constraints associated with that size of the set. And this is the general formulation. So this problem, as I have mentioned already, is very practical. I mean, if you work for any of these companies, you will face this type of problem. I will say in everyday situation, distribution for HEB, distribution for UPS, Amazon, Dell, Walmart, especially during this COVID-19 situation. So going back to the transportation problem, I have mentioned these words balance and unbalanced already. So let's talk about what a balanced transportation problem means. If the total supply equals the total demand, the problem is said to be a balanced transportation problem. So what I'm saying is the summation of all supply from all supply nodes from 1 to m equals the summation of all the demand from the demand points from j equals 1 to j equals n. If that relationship holds, then we know we have a balanced problem. We go back to our original problem, or this problem. If we add up, basically what that's saying is you add up 1,000 plus 1,500 plus 1,200. This is equal to 2,700. and then you add up the 23,000 plus 1,400, that is also 2,700, then this problem is balanced. That's what this relationship is trying to say. You look at the total demand, total supply. If the number is the same, then we have a balanced transportation problem. And this is the relationship. If that's not the case, then balancing a transportation problem if total supply exceeds the total demand. So how can we make this problem a balanced problem? If total supply exceeds total demand, we can balance the problem by adding a dummy demand point. Okay, so what that's going to do is it's going to help us estimate it's not estimating, but it's going to count the number of units that we are not going to be able to supply. Okay, so we're going to create this node just to being able to quantify the amount of supply that is not going to be able, we are not going to be able to supply. Since shipments to the dummy demand point are not real, they are assigned a cost of 0. Okay, so dummy demand point, supply node, dummy demand point is basically there just to make sure that in this case, we have more supply than demand. We are not shipping anything in reality. We are just using that demand point to quantify how much we have on excess in this case. So on the opposite side, if we, yes, go back.
If you don't find out how much excess like more we have,
Mm-hmm. Yeah, so the idea is that with the addition of the dummy demand point, yeah, we're gonna balance the problem. Okay, but the meaning, let's say this is our dummy demand. So we have 1, 2, 3, 1, 2, 3, and this is dummy. So we have 20. In this case, we have a total demand of 2,400. When we solve the problem, 300 units will be sent to this dummy demand point, which is basically telling us, you know, you have an additional 300 units that are not being used or that are not being shipped because you don't have enough demand. On the other side, if we have a different problem, let's say we have a demand of 27 and then a supply of only 20. So this is the supply and this is the demand. Now you have a shortage of supply. So the supply is less than the total demand. If the total supply that is strictly less than total demand, the problem has no feasible solution. You are not going to be able to meet the demand. If you remember the constraints for the demand, right? You have to at least meet that minimum demand. If you don't have enough supply, there's no way for you to satisfy those constraints. So what we do is that we, again, have no feasible solution. One or more of the demand will be left unmet. So generally, in such situation, a penalty cost is often associated with the unmet demand, and the total penalty cost is desired to be minimum when solving the problem, right? So what we are trying to say, like from a practical point of view, you know that you're gonna, if you face a situation in which you have less supply than demand, typically you have a contract associated with these customers. And if you're not able to satisfy the demand that they need, there is a cost penalty associated with not fulfilling their orders. So that's a cost that now you have to take into consideration also as part of your solution. So let's say each demand point has a different penalty cost. For some customers, the penalty cost is higher than for others. When you solve this problem, you want to make sure that you still minimize the cost. So you're going to try to meet the demand of those customers that have a very high penalty cost. So you don't, you still solve the problem and you still minimize your cost. So from that perspective, let's look at this problem. You have a question? In the MG model, suppose that the Detroit plant capacity is 1,300 cars instead of 1,500. Total supply equals 3,500 is less than the total demand of 3,700, meaning that part of the demand at Denver and Miami will not be satisfied. So now you have this situation. You have 2,700 instead in terms of demand, but you're making this guy. So this is 3,700. So now you only have 3,500. If total supply equals total demand, the problem is said to be balanced transportation problem. Because the demand exceeds the supply, a dummy source plant with a capacity of 200 cars is added to balance the transportation problem. So we use the same strategy. Now we add a dummy node into our network. The unit transportation cost from the dummy plant to the two destinations is 0 because the plant does not exist. So if we solve this problem, actually we can try to do that in Excel. If you have your computer, let's try to build this problem in Excel. I think I have here. Okay, so we have the information at the top of this problem. This is for the balance problem. We have the mileage and we have the transportation costs, transportation variables. This is the actual solution. So let me take this out of here. Our objective function is in terms of the cost associated with shipping from each one of these source nodes to demand nodes. And then we have the constraints. Should be this or equal to. Right, so this is same thing that we are observing here. So Okay, so we have 1,000, 1,500, and 1,200. And we have the demand constraints 2,300 and 1,400. And the constraints again for the supply constraints, we are adding X11, X12. So that's what we have here. And for the demand constraints, we are adding the columns. So 11, 21, 31. Yes.
I don't think this is straight.
No, I can make it available. Yes, let me do that. So everybody has the file. Files. Resources. Have that already here. Okay. So it should be available in today's module. If I click in the solver, we are minimizing the objective function, and then we have two group of constraints. Solve this. There's no issue. This is a balance problem. So we end up with a solution in which we are distributing from 1 to 1, 1,000 units, from 2 to 1, 200, 2 to 1, 1,300, 2 to 2, 200, and then from 3 to 2, 1,200. And this is the minimal cost. You see all constraints are satisfied. Even if you define them as equalities, you'll see that the left-hand side and the right-hand side are going to be the same. And this is the balance case. The issue now, we look at the unbalanced scenario. Take this here. Zero. And if we go to the solver, our constraints are defined as equalities, just to illustrate the point. Okay. We're taking B12 into account. Here. Yeah, I'm editing this just to illustrate the point. So now we have a non-balanced problem in which we only have 3,500 demand and 3,700 for the 37 for the demand, 3,700 for the demand, 3,500 just for the supply. If I try to solve this problem, it should give me a solution that is not feasible, right? solver couldn't find a solution because I don't have enough supply to meet the demand. Okay, so how do I solve this problem? If you see, I have added a third row to the decision variables, and that is representing the arcs between this dummy supply node that I'm creating to serve that additional demand that I'm not able to supply, right? So this is what I'm trying to say. This is the case that I'm trying to model now. I only have 3,500, not enough to supply all this demand of 3,700. So if I try to solve this problem, I'm going to get an infeasible, not feasible solution. Okay, so now I need to add this fourth supply node, which is going to be a dummy node that is going to be representing this source plant with a capacity of 200 cows. It's added to balance the problem. The unit transportation cost from the dummy plant to the two destinations is 0 because the plant does not exist. So if I do that, I'm gonna be adding this dummy node to my problem. Okay, so I'm multiplying that per decision variable. That's good. I have a supply constraint that I need to add. So this is going to be looking at this. This is going to be looking at these two. This is going to be looking at these two. So I have a supply constraint number 4 now. That is going to be equal to this plus this. And this is going to be equal to 200. So I'm adding that extra supply constraint to balance the problem. Now, if you add these numbers right here, that's going to be equal to 3,700. And I need to also add that to my demand constraints. So I'm going to be adding all this, including now this dummy node. And I'm going to include this dummy node. So I have now a problem that is balanced. Supply and demand is the same. The cost associated with each one of them is the same. I'm adding a dummy node with 0 cost. I'm calling this from here. Yes, I can actually do that. We can call this from here. And I can try to solve the problem now. See if this works. If I go to data, solver, I want to change or edit my constraints. So this is for all this, all this. Sorry. And then this one. So if I solve the problem now, I can get a solution. And you see that there's a number associated with the dummy. This is basically saying that my demand, or let's say in this case, Miami is the one that is gonna get penalized. I'm not gonna be able to supply 200 units to Miami. Why do you think that's the case? Why is Miami penalized instead of Los Angeles? I'm sorry, instead of Denver.
Farther away.
Yes, and that's reflected with the cost, right? So so it's cheaper for you to ship to Denver than it is to Miami. So you're absorbing that since we don't have a penalty cost associated with this yet. It is cheaper for you to ship just to Denver, fulfill Denver instead of Miami. You see the cost from Los Angeles to Miami is $215, where when you look at the cost associated from Los Angeles to Denver, it's just 80. For Detroit, it's the same thing. It's less expensive for you to ship from Denver to Denver than to Miami. The only case is for New Orleans, in which it is cheaper for you to ship to Miami than to Denver. Okay, so question for you now is, if you were to make sure that Miami is not the one getting penalized, what would you do? We thought right now what we are showing here is just the cost associated with transportation. We are not taking into account the cost of a penalty cost associated for not fulfilling the demand. So for instance, if we were to penalize, we can use this cost here to include a penalty cost. Let's say we make this penalty cost higher than the difference of this cost. I think that should work. So right now there's a $34 difference shipping from, oh, not that, because this is benefiting Miami. So let's say we make it $9 penalty cost associated with this guy. And then I try to solve this problem. Yes, there you go. So now we're just making a $9 penalty cost associated with Miami. You see that no longer penalizing Miami, I'm gonna be penalizing Denver instead. That makes sense? You see how that works? You look at the cost of Detroit, it's less expensive for you to ship from Detroit to Denver, but the difference is just $8. If I add a penalty cost associated with not shipping to Miami of $9, that cost will become higher than the difference in the cost of shipping. So by just adding that penalty cost, my penalty cost is at least $9, my decisions will change. Okay, and that's a way for me to make sure that I'm not penalizing one of the nodes. And the model will do that for you. We will have this penalty cost already as part of the contract. So you will input those penalty costs here. And then the decisions will be made based on those costs as well. Questions? Hope this makes sense, right? So you see with the numbers how that unbalanced problem becomes balanced. Now we see that one of them is getting a shortage of supply. But we are also seeing that if we plan for the associated costs, penalty costs, we can force the model to serve a specific demand point, which is what this is showing. Okay, so So before I added the penalty cost, this was the solution that I showed you. You were seeing Miami getting a shortage of 200 units. So that was the original solution without the penalty cost. If we add a penalty cost, which is trying to answer this question, the dummy plan ships 200 cars to Miami, which means that Miami will be 200 cars short. Can you modify the model to make sure that a specific destination does not experience shortage? The answer is yes. If you look at the costs associated with shipping and penalties, you can find a way to make sure that one of those is not a specific destination that's not experienced a shortage. Okay, so now last thing we're going to do today, so we were going to have time to go to the integer programming, so we're going to leave that to next time. But last thing we're going to do today is talk about briefly about the assignment model, which I mentioned this is a special case of the transportation problem. The classical assignment model deals with matching workers with varying skills to jobs. So let's say you're in a makerspace, you have all these people working in the makerspace. Some of them have specific skills and you want to assign them to different jobs. This will be the model that you would use. So this model assumes skill variation affects the cost of completing the job. So the goal is to determine the minimum cost assignment of workers to jobs. So the assignment model, again, you're going to have a cost associated with workers and jobs. So this could be supply and demand, right? Same idea. With the only difference that now our constraints are going to be zeros or one. Okay, so we have a job and we have an available worker. Once we assign a worker to a job, that worker is no longer available. Once we assign a job to a worker, that job is no longer available. So the general assignment model has n workers and jobs. The element Cij represents the cost of assigning worker I to job J. The assignment model is a special case of the transportation models. The workers represent the sources and the jobs represent destinations. The supply demand amount at each source destination is exactly 1. And the cost of transporting workers to jobs is Cij. And that's going to be looking, for example, this is a steel worker. Salary of this steel worker is higher than salary of an average worker, for example. So that would be the cost difference between these workers. And the assignment model can be solved directly as a regular linear programming model. I think that's the end. Any questions? There's no questions, then we'll meet again on Wednesday. That'll be our last lecture before, actually, no, we have another lecture before Thanksgiving. But after, so we had lecture on Wednesday, we have the lecture on Monday, and then after Thanksgiving, we're gonna have our review for the third exam. And on Wednesday after Thanksgiving, we're gonna have our third exam. Remember that if you are happy with your grade after the third exam, you don't have to take the final. So the final is optional. Final is cumulative, is optional. So we'll talk about that during the review after Thanksgiving, but keep in mind that if you do well, you're happy with your grade after the third exam, then you don't have to take the final. Any questions? That's it's a university. Yes, but the university is closed on Wednesday, I think. Yeah. Monday, Tuesday. Yeah. Yes. So you're basically next week will be Monday, Tuesday, regular operations, and then Wednesday it goes as a holiday. Yeah. Any questions?
So, I'm sorry.
Yes, yes.
So we're gonna have a lecture Monday.
We're gonna have lecture on Wednesday this week, and then on Monday.
Okay.
Wednesday is the university is closed, and then we have Monday after Thanksgiving the review, and then Wednesday the third exam after Thanksgiving.
And then after the third exam, that Wednesday, how do you determine, for example, if someone has to take the fourth exam or not?
You will see I will grade everything. I will post your grade with the information that I have at that point, then you'll make a decision. And I mean, you don't have to let me know if you're gonna take the final or not. The final will be here. If you show up, you're taking the final. If you don't show up, you tell me that you're not gonna take the final. So that's easy for you. It's a Saturday morning, yes. Yeah. Yes.
Feel like such a weird, I don't know.
It is because